Okay. As I mentioned, this is the last lecture of any new content in terms of what is going to be on exam 3. So, Wednesday and the 3/4 of or 2/3 of Friday will be review for exam 3, and Friday end of lecture first group will go, and then next week everyone, the other 9 groups will go. And those are also new content, but that will not be on exam 3. It's just for you guys to kind of see what would be next. Okay. So we are on caching. And we have gone through what is spatial and temporal locality, why we have this memory hierarchy, direct map caches, how to access a cache, what to do when we have a cache miss, what do we do when we have a cache write, it takes longer than the cache read. And we've also talked about beyond a direct map cache, set associative caches, and introducing more levels to the memory hierarchy with multi-level caches. And today we're going to talk about the interactions of caching with keys and software. What is the real impact of caching? And we're also going to recap some of the key cache concepts. Right. But as we talked about already, there are out of order CPUs, right? And these CPUs can execute instructions out of order. It doesn't matter if the instruction ahead hasn't finished, as long as there's an instruction in front of it that will be fetched that is independent of it, why not execute it, right? So rather than just stalling for those hundreds of cycles when you have a cache miss, the out of order CPU can try and find some instructions ahead that are independent that it can execute. So this provides some of the performance hit of getting a cache miss. Because as we saw from our equations, memory is hundreds of times slower than the cache. So we would have hundreds of cycles of stalling if we did not have a way to fill in that gap. And beyond out of order CPUs, one of the topics that one group is working on is simultaneous multithreading, right? Or simultaneous multithreading. You guys will talk about simultaneous multithreading and how it's very similar. All right. So the other aspect is the effect of the miss depends on the program data flow. So if you have lots of dependent instructions and you can't find independent instructions, then the out of order CPU may not help. But if you have multiple threads, like in simultaneous multithreading, one thread gets stalled because of a cache miss. During those 100 cycles, new thread comes in and uses up the CPU during that time. So this is what makes it kind of harder to analyze these programs, but you can use simulation, functional simulation, to figure out what the performance might be. The other thing was with interactions with software. It's not always easy to understand the implications of caches. Okay. So we all learned about big O notation, right? And the trends as data size increases. or your algorithm input increases, right? So here are two sorting algorithms, radix sort and quick sort. And this is the theoretical graph. So just by big O notation. Right, radix sort. The larger number of sizes, and then quick sort, larger number of sizes. But if we actually use a real CPU and measure performance based on these different number of items to sort with quick sort or radix sort, then we can see that in actuality, we are the right shape and the right shape for this, but we don't perfectly match. This can be because of a lot of reasons, but one of the larger reasons is because of caching. So your misses in caching is going to depend on the memory access patterns. And memory access patterns are determined by your algorithm's behavior. Am I streaming data? Am I randomly accessing data? And also, does the compiler optimize for memory access? And the other thing is the programmer can also optimize for memory access. If you are streaming data and you have this giant matrix, that's say 10,000 by 10,000, your cache is not going to be very happy about that giant matrix. It's not going to fit in the cache, right? Cache is megabytes of data. That giant matrix is all, say, 32-bit integers, beyond megabytes. Might be close to a gigabyte, right? So one thing that the programmer can do is not just take advantage of spatial locality with the cache, because spatial locality, as you fetch, you're fetching ahead, right? But if you need to reuse, then you need to also take advantage of temporal locality. So if I'm doing matrix multiplication, I am reusing things, right? So one thing you can do as a programmer is, rather than streaming through the whole matrix like you would normally do by hand, right? You can break it up into smaller squares. And if your squares of the two matrix fit into cache, then you can do that small square very fast, right? You do a lot of loads, and then you do a lot of computation, and then you do your stores. And you go to the next square. So this is something that is called tiling. The compiler will not do this optimization for you. And because caching is such a large impact on your program, if you use tiling versus non-tiling as a programmer, you can see orders of magnitude faster performance. 10, maybe 100 times faster. So if you remember nothing from this class, tiling and memory optimization is the most important part, because the compiler will not do this for you. Not yet, at least. The compiler will do loop unrolling, right? We talked about loop unrolling. It will do that for you. You don't have to worry about that. But tiling, it does not do for you yet. This is what we just talked about. This memory subsystem performance is often a very critical factor in determining performance of your overall program. So That is why we cannot just solely rely on big O. We need to have some experimental data in order to analyze our performance, as well as this is why we need to kind of hand optimize for caching. So caches give this illusion of a very large and cheap memory with the access time of fast and expensive memory, right? And we have two types of locality, temporal locality and spatial locality. And we have many different design parameters of our cache design. What is the block size? What is the overall cache size? How much associativity? What is our write policy? Are we write back or we write through? And these are all things that the computer architect must kind of balance and combine to minimize miss rates and access times on a wide range of applications. Right? But you as a programmer, if you know the size of what the CPU is, right? You can go to the website of the manufacturer. You can find out what is the size of the L1 cache, what is the size of the L2 cache, what is the size of the L3 cache, and then you can change your for loops in order to do this tiling, to optimize for those CPUs. All right. So for the memory hierarchy, common principles do apply at all levels of the memory. And at each level in the hierarchy, we have these different policies that we talked about. Where does a block go, right? How do we find a block in the cache? Right, so where does the block go? That is determined by index bits, right? Finding a block. Also, you check index bits. Go to that index. Check what?
The tag. Valid and tag.
Valid and tag, right? And then once we found that block, then it's a question of which word in that block do we want, right? And then replacement on a miss. What is our normal policy? Least recently used. If we have very high associativity, like fully associative, and least recently used becomes difficult to implement in hardware, what is a okay substitute policy? Write policy. What does it mean to be write through? Right in the name. Write through. What am I writing through? So what if I'm writing to the cache? What else am I writing to? The memory. So then everything is consistent. Okay. It writes beyond the cache, it writes through it. What about write back?
You do it later and then put it to memory.
It's only when I'm taking it out of the cache that I need to now update memory. Okay. But this leads to inconsistencies between cache and memory. So block placements, right? It's determined by associativity and also the size of our cache. So for direct map, we have one place, one choice. For n-way set associative, once we find our index, we have n different choices. We're going to fill in empty, non-valid sets first, then we use least recently used or random, depending on whatever the policy that was set is. Fully associative, any location. There are no index bits. Like we talked about, higher associativity reduces miss rates, but it is a diminishing return, and it increases complexity, cost, and most importantly, access time. And access time matters the most because usually accessing the cache is going to be on your critical path. So this is potentially going to set your CPU's cycle time. So here's for finding a block. We have direct map. We get the index, the tag we compare to. There's just the one, right? For n-way sets associative, we again find the index. Then we have n different tags to compare. Fully associative, we need to search every single entry in the cache. And our replacement policy, we talked about this already, least recently used. This is complex and costly for high associativity. So think like 8-way and above, 4-way and below. It's still pretty simple, right? So when we have that higher associativity, if we do our experimental data and we find that random is close to the same performance, then we can use random, right? And write through is update both upper and lower blocks. So it's writing through the cache. And it simplifies the replacements, but we may need to have a write buffer. Otherwise, we're going to lock up our cache. Write back, this is what is typically used. It's updating the upper level only. And then we keep track of, was our data written to? They call it, along with the valid bits, the dirty bits. If it's dirty, that means it was written to. So that means that when you evict it from the cache, you need to write that back to memory in order to remember what that written data was. So we need to keep another state, just that dirty state. So we have these different types of misses. Compulsory misses. This is just, I've never had a chance, right? This is the first time I'm accessing this block. Capacity misses. This is due to finite cache size, right? A conflict miss occurs if in a fully associative cache, I would have had a hit. And these only occur in non-fully associative caches. Because if you have a fully associative cache, if it's not a compulsory miss, it's capacity miss. And it's due to competition for entries in that set. So here are a few cache design trade-offs. So if we increase the cache size, we decrease capacity misses because we can fit more data into our cache. But the negative impact is we might increase access time. If we increase associativity, we're trying to decrease conflict misses. But we again might increase access time because now I have, instead of checking 4 different places, just 4 different tags, now I have to check 8. Increasing block size. So this is going to decrease compulsory misses. right? Because I'm going to, when I grab a block, my block size is larger. So I'm pulling more data into my cache. But this is going to potentially increase the miss penalty because for a very large block size, it might increase my miss rate due to pollution. If I'm not going to use all of that data, then I fetched it all for no reason. Right? And if my block size is larger, then I have to take a little bit longer to get all of that data from memory. So here is an example processor. We have 1, 2, 3, 4 cores, right? And directly in the data path somewhere on this core is L1 cache. That's why it's not labeled. But each one of these cores has L2 cache. And you can see that L2 cache is significantly smaller than L3 cache, right? And in this case, they all have their independent L2, L3, and L1. Oftentimes, especially in CPUs nowadays, L3 is shared among multiple cores. So here's a same CPU, and it's being compared with this AMD CPU. This isn't super important for us, so let's go to the first question. It's just in conclusion, right? Fast memories are small and large memories are typically slower, but we want really fast and large memories. So caching gives us illusion. We have locality because programs use a small part of their memory space frequently. And then we have the memory hierarchies, okay? So memory system design is critical for performance because if you have poor design, you can have very poor performance because of the disparity between the speed of L1 cache and memory. So here is your first question. Your code is 502, and do answer this on your own first.
I'll be right back. Can you click the begin on the phone, maybe?
Should be. Oh, sorry. There. Right. Okay.
Did you get the final review? Check.
Right. Are you guys all done answering this individually? Okay. So, let's see. Most of you are answering D. So, yes, let's just go over this one together. And answer each one of these things individually, right? So increase to two-way set susceptibility. Is this going to help me or not? No. Why?
Because they're not fighting for memory space or memory locations, like, it's just a sequential access.
Mhm.
So like, if you were accessing two memory locations at the same time, maybe you have like a conflict where they're trying to evict each other or something like that. Or if you're accessing two different locations, like back to back, then
Uh-huh.
it would evict each other, but if you're just doing it sequentially, like, it doesn't matter.
So in summary, we have sequential memory access and there's only one memory stream, right? So this subjectivity is not going to help us. What about increasing block size to 64 bytes?
Yes.
Why?
The spatial locality of an array, a bigger block size you'll be accessing. Then sequentially, which means you'll get more hits for every time you need to.
So I'll fetch more ahead
Mhm.
when I do have a miss. And because we're sequential, like you said, the next one is going to hit
Same space area.
until we get another miss after we've depleted full. So we like B. What about C, increasing the cache size to 64 kilobytes? Oh no. Make the cache bigger. Helpful or not helpful in this scenario?
Not helpful,
Not helpful, right?
just because you have more space, but you're accessing it, I think, sequentially, so it would
Yeah.
help.
I'm not reusing anything.
Yeah,
So sure, I can store it for a bit longer, but so what, right? I'm not coming back to it. It's just going to be overwritten by whatever is next. Anyways. So we liked B. We didn't like A, we didn't like C. So should just be B. Right? Right, so we have one more. So it is a little bit different now, our for loop. But we have the same catch and the same question. So you can answer this on your own first. don't see answers changing anymore. We thinking about this individually. Okay, so you talk to the people around you. We have a larger portion of people getting this one right this time, so I think parent instruction can work.
What do you think again? I think that this one, because it's that nested valley, everything. So there's like, and then the cash size would help as well, because each array is to everybody.
Yeah,
Instead of only being a fit.
that's the thing, yeah. I just don't know.
You have to like do the math, because like, well, it tells you like each array is 32 kilobytes, it's like good. So it's, and you can use. And then you lost it, is 4 bytes per person, and then the actual. Each block has. Because there's 32. Every locations. Yeah. And the one right. And you do something. I was missing a scale. Like it's double 40. Just like the first 4 versus that numbers, and then you reset.
Yeah, yeah,
And like really see, would you, how you come back to it? That's a good one. It's not that new. Like 10:30. I was in the shower and I was like, wait. Sure.
No, like.
Question is, will it use an memory?
I don't see answers changing anymore again. Are we done with the peer instruction?
If you do it again.
yeah.
Okay, so again, one at a time, I want to hear from new people. Increasing to two-way set associativity, yes or no? Yes, what?
Because in the last one, you're accessing everything for like memory, but then in here, I believe you're accessing the memory, so that'd be A.
Yeah, so we have two different memory streams. Right? So now we have potential to fight if we have direct map. So if we have two-way set associativity, now we have one set can hold the other one set can hold the other one, right? So we like A, it would help. And again, someone else, increasing block size to 64 bytes. Come on, you guys have this answer right. Okay, my electrical engineering students, my one electrical engineering student, what do you think? Yes?
Yes.
Why? Why was it here? What was the reason? Yes. So is it any different here? It's not different. It's still spatial locality. We're still decreasing compulsory misses, right? So we like this step. What about increasing the cache size to 64 kilobytes? This one is the one that is going to take a lot more explaining. So first, do we like it? Okay, why?
You want me to answer or do you want?
Yeah,
somebody else?
you can
Okay.
answer. I don't think it's gonna be too hard.
Well, the first thing we have is we are going through a double for loop, so we are coming back to the memory locations. So there's a possibility we can take advantage of temporal locality by reaccessing the same amount of memory. And then you have to do the math on whether we would.
Yeah.
So there's 4 bytes per 32 byte block. So
Uh-huh.
that means 8 pieces of information per block. And then there's 1,000 blocks because there's 32 kilobytes of cache and 32 byte blocks. So that's 1,000 blocks total. And then that gives you, it can fit essentially 8,000 pieces of information in each, not in each set, there's 2 sets. So it's like the first set will have 4,000 pieces of information. The second one will have 4,000. So it doesn't fit the entire thing in there. You double
We need
that.
to fit 8,000,
You
right?
need to fit 8,000,
Yeah, so then,
If you double it, then now you can fit the 8,000 possibly. I didn't do the exact math, but I think that way, if you roll the loop again, you might have all the memory still there and you solve it.
so even though you didn't do the math exactly, it does exactly. And you can do it very quickly, right? This is 8K, right? If you're in terms of power of 2, which we are, right? Times 4. Now it's 32K, right? 32K is the total size of our cache, which is so I can fit half, right? So what happens if I have 32 kilobytes is I get halfway through this inner J for loop and my cache is full, right? Then I come back to the top of the cache and I replace everything with the other half. But if I double to 64K, when I'm halfway through this for loop, I'm halfway through the cache. Okay. And then when I'm full all the way through the for loop, everything fits absolutely perfectly in the cache. And then the next iteration of this for loop, everything is in the cache. Okay. So C does help. So we like A, B, and C combined for this example. For those of us that's still answered C, but didn't quite have the explanation part, is the explanation parts better now? Yes, no, yeah.
Could you go over one more time, please?
So let's just start with 32 kilobyte cache. Yeah, right? So what we're first going to do is calculate what is the size of A, what is the size of B. Okay. So we have 8K elements that we're looping through. Each element is 4 bytes. 8K times 4, 32K. So each one of these arrays is 32 kilobytes of data. But my entire cache is only 32 kilobytes of data. So when I get to the middle part of the for loop J, so around 4K, I have filled up my entire cache. Okay, because I have half of this, half of this. So I'm through 16K here, 16K here. So that's 32K. But I still have 16K left, 16K left. So now on the 4097th iteration of this for loop, I go back to the first index I was at. And I check the tag of this string. It doesn't match what's in the cache. I need this data, but the data from array A at index 0 is in that spot. So they're now competing for that spot. And I have a capacity mix. So I fill in that top spot with array at J at 4097, array B at 4097 and the other spots. And I do that replacement for the entirety of the cache. So now my cache holds the second half of both of these arrays. I come back to this for loop, right? Now I is 1. J is again 0. So I need array A at 0, array B at 0. But I check the tag. What's in that spot instead is array J and array B at 4097. Which is not what I need, right? So again, going through the entire first half, I evict everything. And we fill it in with the first half. And this just keeps happening over and over and over again. So that's 32 kilobytes. Okay. If we increase the cache size by doubling it, now I can fit 64 kilobytes. So this is 32 kilobytes. This is 32 kilobytes. After I go through one full iteration of this for loop, everything is in the cache. Nothing gets evicted. I come back here, I is 1, J is 0 again. I'm looking for A at 0, B at 0. It's a hit. It's in the cache because the entirety of it fits. Better? So you see how we had to do a little bit of math, the process for it, but we did find out eventually that increasing this cache size does help. Okay. So any questions on these caching questions?
It goes back to like the compulsory versus the conflict. So even if like the spaces are like, let's say they're full, but it's like the first time I'm accessing a block, would that be a compulsory or would that be a conflict?
It's the first time I've ever accessed this block, it's compulsory.
Okay, so that would be.
So the first iteration of these are all compulsory. So when I is 0. But if I'm 32 kilobytes, when I is 1, I have all capacity misses. Because I've seen all of these memory references before. The only reason they're not there is because my cache is too small. And they're not conflict because I've accessed enough data to fill in the cache in between. Any other question? Okay. So there's no reading for next time. And again, just as a reminder, Wednesday, review, Friday, mostly review. We'll hear from which you guys,
Seymour, yep.
and you guys
Register renaming.
register rename. Okay,
Homework is also due on Wednesday.
yeah.
It's 6 weeks.